Hello, everybody, and welcome. We are NASA's Space Mission Concept Academy, Team 31, also known as T-T31. We are presenting our preliminary design review for the Enceladus concept mission. Our team consisted of 10 people, and we were divided into 3 sub-teams, which included the science team, the administrative team, and the engineering team. Life on Enceladus? Maybe. There were previous missions that discovered more information about this Saturn moon. Voyager and Cassini. Voyager had its first images of Enceladus in 1980, and Cassini had flybys in 2005, 2008, and 2015. Through these missions, we discovered the tiger stripes in the plumes at the South Pole, which might show that the ocean beneath the surface of Enceladus is warm enough to promote life. We also saw that Enceladus is mineralogically diverse, and these minerals could mean life as well. There's also possibly a global ocean, and our mission will seek to confirm that. Our mission parameters for Tigger-1, that's the name of our lander, were that we needed to land in the Tiger Stripe region. We also needed to conform to the mass constraints and volume constraints so that the lander would fit inside the orbiter. And we had a budget cap of $400 million or less. We decided to go with a seismology mission and analyze the interior of Enceladus. Also, we're relaying data safely to Earth, and we're providing model validation. This is because so far we've only had flyby missions of Enceladus, and we have yet to put a lander on this Saturn moon. Moving on to Leo, who will present the concept of operations.
The concept of operations is drawn in stages labeled 1 through 8 and begins with stage 1 with a plan to enter Enceladus sphere influence on the 23rd of October 2026. Once they're in range of Enceladus, the orbiter and lander will separate with the lander headed towards the surface of Enceladus and the orbiter continue its orbital path, at which time the orbiter will then act as a relay to transmit data between the lander and Earth. As the lander descends, it will close any applicable valves to keep a vacuum and continue on to landing. 15 minutes after landing and debris is settled, it will be ready to conduct surface science collection. And now on to Nathan.
For the descent maneuver, we wanted to go with something as simple as possible, both conceptually and computationally. Therefore, we chose to perform 2 burns, one to cancel the horizontal velocity of the lander while it's in orbit, and then one to cancel the vertical velocity after a period of free fall. The vertical burn is a suicide burn, which times the burn such that the lander reaches 0 velocity exactly as it touches the ground. This is the most fuel efficient and gets the lander on the ground as quickly as possible. To calculate the burn timing, we used an algorithm which utilizes numerical analysis to compute the proper time to start ignition. And now on to Sebastian for the lander design.
Thank you, Nathan. So Tigger-1 is mainly made out of titanium due to its high yield strength of 880 megapascals and its small coefficient of thermal expansion. Also, you can see in the top of the lander that we have a Johnson solid that is made out of a square base and 3 equilateral triangles. In the bottom, the thruster is fixed to a 3-axis gimbal that will help with the two-burn descent maneuver. Handing it off to Jacob, the lead scientist.
For payload design and science instrumentation, we have 4 systems: communication, data handling, data collection, aka the instrument, power. So basically, we need power to power everything in the lander. Our subsystem, so communication systems, this is a very important system because our data collector is useless if it's not communicated. Our instrument works according to established procedures, closely to the Mars InSight lander. Our manufacturing plan is commercial off the shelf. performance characteristics, basically, it's the temperature is very important. Our instruments work according to a certain operating range, so thermal control is very important for the harsh frigid temperatures of Enceladus. We would like to land at the autumnal equinox, which is corresponding to the radius of perigee. And so basically, this, based on the time that we're going to leave and the time it takes to get there, then this is the autumnal equinox is when we're going to get there. That's for Saturn. And so our Saturn's payload objectives include seismometer data, and this is for like model validation and other science objectives. And now on to landing site. So our landing site that we chose, the key parameters include the slope, proximity to the tiger stripe, elevation, and landing site radius. So we chose landing site 1 because it had the small slope, a small proximity to Damascus Sulcus. It had a low elevation, and it had the second largest radius, which corresponds with one of the requirements in landing within 15 meters of the landing site. Now on to Cavell.
We designed our communication and data collection systems around redundancy and reliability. During data transfer to the orbiter, we transmit simultaneously from 2 antennas to prevent outages from disrupting communications. And in data storage, we have 3 methods to reduce risk of data loss. We have radiation shielded hardware, solid state data storage, and we use a RAID configuration with error correcting codes to store the data. Next, on to Matt.
Thank you, Cavell. While our team addressed the full range of risks in our proposal, our team also highlighted these key risks. For the lander and design and operations, we considered that temperature control of the battery and the radiation exposure to the lander was an important factor to consider in this, the effectiveness of the mission. To resolve those issues, radio's isotope heating and radiators, as well as radiation hardened components, are included within the design. For payload design and science instrumentation risks, we addressed instrumental and or power failure. In addition to the redundant sensors incorporated into the SLED instrument, power will be rationed to the data handling and transmission systems to maximize data collection. For environmental hazards, we took into consideration the landing location of the site. We balanced factors such as maximizing data collection and science opportunities with proximity to the active plumes. For unstable terrain, we equipped our lander with a landing camera to avoid obstacles, and the seismometer can account for up to 15 degrees of tilt. For testing hazards, we also considered software testing and damages from physical tests. These can be addressed by software management, diagnostic tools, and replacement parts, as well as following implementation procedures. Now we will move on to Anna.
All right, so our mission consists of 5 phases. Phases A and B we finished as of today, which were our concept development and preliminary design. We are kicking off phase C and D January 5th, which will be our final design and fabrication, which consists of manufacturing and our critical design. And that will go until our launch, which will kick off phase E, which is on October 31st, 2023. We will travel to Enceladus for upwards of 3 years until our landing date, which is November 6th, 2026, and our mission will close on our closeout date, which is December 21st, 2026. To summarize the T-T31 mission, our mission itself is to map the subsurface structure of Enceladus. Our method is seismology, and we have 4 distinct goals. First, to analyze the ice shelf, which includes density and thickness. Second, to confirm the existence of the subsurface ocean. Third, to successfully relay all data safely back to Earth. And finally, fourth, to provide model validation, since our current knowledge of Enceladus is mostly based on models. And on behalf of Tiger Team 31, thank you for your time and have a great rest of your day.